Hello and welcome. This is Michael Marceau, and in the short video clip I'd like to go over lab number 1 with you, diode characteristics and operation. Also I'd like to cover the IV device analyzer that you'll be using for this lab. First of all, diodes are polarized. That means they have a positive terminal and a negative terminal. In most cases they will have a band on one end signifying the cathode, which is the negative terminal. In the case of LEDs or light emitting diodes, there's a flat spot on one side indicating the negative connection or cathode. However, there's also a longer lead, and that indicates the positive connection or the anode. So you may want to spend some time taking a look at the diodes so that you can identify the anode and the cathode. In the first part of the lab, you'll be looking at manufacturers' data sheets in order to obtain specific pieces of information. In the second part of the lab, you'll be using the IV analyzer in order to obtain a set of characteristic curves for each of the diodes. In Electric Circuits 1, we took a look at this. We had a basic setup here including a variable voltage power supply, an ammeter, a voltmeter, and a device under test, which is called a DUT. In this particular case, we have a Zener diode here. You can tell because of the different characteristics in the symbols, or in the symbol for the diode itself. In electric circuits, we set the voltage to a particular value, measured the forward current, and measured the voltage across the device under test. In this way, we were able to collect a series of points and finally plot them on an IV plot. The purpose of the IV analyzer is to provide an automated means of collecting this and displaying this information. So as you can see here, we have the voltage source, we have a current monitor, the DUT or device under test, and the voltage monitor here. The IV analyzer uses a slightly different setup for this, but the results are basically the same. You will notice that for the power supply, we use an op-amp to provide additional current for the diode. We use a current sampling 10 ohm resistor to help us monitor the current, and you'll notice that we have a voltage monitor over here, which is the difference between one end of the diode, the voltage at one end of the diode, and the voltage at the other end of the diode. So basically, we are collecting all the information we need, and it's the same information that we obtained in electric circuits. A test jig has been provided to you and will be provided by your instructor. When in operation, the IV curve tracer will look something like this. The graph part in the center part of the display will give you the IV characteristics. Over on the right, you'll see that continuous sampling can be applied to the device, but we will not make use of that feature. Persistence will allow each of the data points to be retained on the plot while a new point is taken. You may want to enable the persistence so that you get the characteristic curve rather than just observe the points. When completed, you can clear the plot by pushing the Clear Plot button. The next set of inputs provides a sweep range for the voltage. -10 is fine. The positive end, you might want to change that to 3 volts so we don't burn out the LEDs, and the number of samples you can leave at 100. When ready, just push the Go button, and the software will take it from there. There are a variety of indicators on here as well. You'll notice over on the left is the current, and there's a scale for the current. Down below the graph is the applied device voltage and the calculated device power, so that you can actually see how much power is going into the diode. Down below is the voltage, and this slider you can actually move if you wanted to set the voltage at a particular value. Alright, now we're ready to start the device. Go ahead and plug your MyDAC unit in if you haven't already, and make sure it's recognized by your computer. That may take several seconds. When that's done, go ahead and download the IV Curve Tracer program that's loaded in Moodle. It's a very short file and won't take very long to download. When ready, make the changes. I'm going to change that to 3 volts. We're going to enable persistence, and we're going to click the Go button. If you get the following error or an error similar to that, do not be alarmed. We need to make some changes because of the ports that were used when the program was originally set up. So go ahead and click Stop, and you'll notice you'll be taken to the block diagram for the IV program. And you may notice that one of the blocks has a marquee going on it. We will need to replace this block so that we can use the program with our setup. First of all, right-click in a clear area just below the original block. This is an output block, so select Output and DAC Assist. Place the block below the original one. It will take a few seconds for it to build the input panel. Okay. When the Create New panel comes up, click on Generate Signals, Analog Output, Voltage, and AO0, and then click Finish. When the new dialog box pops up, the only change you will need to make here is down in the sample generation mode. Instead of End Samples, click on the drop down and select the top one sample on demand. Once you do that, then click OK. Once the new DAC Assist has been built, then you can delete the old one by simply selecting it and clicking Delete. Now you will have a broken wire here. If you do Control B, it will take care of that broken wire for you. Now we'll need to run a new wire between that block and the new DAC Assist block. Okay. Now this one is all ready to go. Now we will also need to replace the input block over here. To do that, again, right-click, select Input, and then DAC Assist. Place this DAC Assist just below the old one. Okay. For this one, we're going to acquire signals, analog input, and voltage. Now you'll need to select AI0, and holding your finger down on the Control key, select AI1 so that both AI0 and AI1 are selected. Now click Finish. Alright, that should be the only change you need to make on this panel. Now click OK. Alright, now we need to replace the top block. First of all, we'll delete it by selecting it and clicking Delete. We'll do Control and then B to clean up the broken wire. And finally, we'll run a new wire between the DAC Assist that we just added and the block. Now we're good to go. Now to switch back to the dashboard panel, do Control E. Okay. Now we'll need to restart the program, so we're going to click the play button up here. Okay. Now it should run as advertised. So again, make sure persistence is enabled. Change the upper voltage limit to 3, and now click the Go button. And now you see the indicators are working. We have the maximum current here. Device power is displayed here. The voltage across the diode. And we're done. Now you will notice that for this diode we have both reverse bias and forward bias characteristics. You'll notice that since it is a Zener diode rated for 5 volts, we're coming in a little bit below that. Alright, this is probably a 3 volt Zener that got put in the wrong bin. But you'll definitely notice a forward bias turn on characteristic. Now you can change the scale on here by simply clicking on the values, deleting what's there, and changing that to say 3 volts. Okay. You can also change the end scale over here to something more reasonable, say -5. Okay. Now what you can do is you can use the snipping tool to cut and paste the characteristic for the Zener diode and put that into your laboratory report. You'll notice that when the program ended, the diode was consuming approximately 38 milliwatts of power, 38.117 to be exact. Alright. Now, once you have the characteristic for this diode, you can very easily swap out with another diode. Push the Go button and obtain another plot. Thank you all very much.